So we're still on this serverless topic, and will be for another number of weeks. And I guess essentially this week, this is the lab that you will be working on. Some of you may have already started into it, which is great, but officially, kind of, this is this week's lab. And I'm working my way through this set of slides here. So we have an overall sense of what this serverless idea is all about. And we then started to focus in on the AWS cloud platform and talked or mentioned the various serverless services that they provide. And we're just going to work our way through a small subset of these over the next couple of weeks. And so I started looking at the Lambda service the last day, which is one of AWS's serverless compute services. There are others though. And so what Lambda allows us to do is essentially deploy something as granular as a function to the cloud. Prior to serverless, you had to deploy either the entire application or possibly a container. We talked a lot about containers in the previous semester. So you could maybe deploy a container to the cloud, whether the container contained an entire application or a subset of it. But with Lambda, we can actually deploy something as small as an individual function. And let's see. So we just talked about the anatomy of a Lambda function, which I'll come on to again today. The configuration of the Lambda in terms of its underlying compute requirements, although we specify the compute requirements in the case of AWS anyway, we specify it in terms of how much RAM memory it requires. And from that, the Lambda service then determines the virtual CPU credits that it needs. And obviously that's a tuning aspect of Lambda. You know, when you write a function, you test it obviously to make sure it works properly, but you also see how much memory, how much RAM memory it consumes during its execution. And if you're over provisioning it, then you reduce the amount of RAM memory that it requires, and thus you reduce the cost associated with the execution of the Lambda. The Lambda, I think if we look at maybe if we look at this image here, the Lambda we said as well, technically kind of what happens behind the scenes is that the AWS Lambda service essentially creates a container, although in Lambda's speak, it's referred to as a micro virtual machine or micro VM. So, I mean, I kind of represented this as a box the last day. So it instantiates a micro VM, then it loads your function into that micro VM. It also loads it with its operating system requirements and its other dependency requirements, like third-party libraries. Loads those into the micro VM, then loads your function and executes your function within this box or this micro VM. And essentially, when the Lambda function has completed its task, it just throws away that micro VM. And the next time it needs to run that function, it goes through the whole process of creating an instance of the micro VM, et cetera, et cetera. Also, what we know is that it's how do you cause the execution of a Lambda function? Well, it's event driven, we said. So an event occurs, the source of the event could be many things. could be other, well, invariably it's other AWS services that trigger the event. And the event then is sent to the Lambda service, and the Lambda service matches that event with your Lambda function, and it goes through this process of setting up the runtime environment for the Lambda function. So I think where I kind of left off the last day was I was about to give you a quick demo of all of this. And so the demo is as small as we could make it. Again, it's a CDK project. So I've got it here ready to demonstrate. So again, as I said, it's a CDK project. So my folder structure here matches the folder structure of any CDK project. So even in the case of the EC2 and ALB project that you hopefully provisioned last week or the week before, it had the exact same kind of folder structure. And we know now that in the lib folder, there is a file for each stack that makes up your CDK application. My CDK application in this case is just going to comprise of a Lambda function. And if I go into this stack file, then we can see, if I just collapse this, again, my stack file, I have a class which is an extension of the stack class. So we're back to the language of the CDK now again. So here's my stack class, and in terms of the resources that I want to provision, it looks like that I want to provision a Lambda function. Now, fortunately, the CDK library provides a nice convenience class called Node.js function, which, as its name suggests, is a way of provisioning a Lambda that runs on top of the Node platform. So again, to use the language of the CDK, this Node.js function is an example of an L2 construct. Every L2 construct, and there are tons of them, probably in the, well, maybe not in the hundreds, but certainly a large number of them. These constructs, they have the same kind of signature in terms of the constructor. You have the scope parameter. We want to associate this Lambda function with the current stack, an ID for the construct, and then the rest, which is this part here, is the configuration settings that are particular to that type of construct. And I think I would have, from recollection now, I might have actually already explained this the last day, but so be it. So because this is a Lambda function, and in particular, it's a Node.js kind of Lambda function, then we're telling it things like what kind of architecture, hardware architecture, do we want to run this Lambda function on? What's the runtime environment for the Lambda function? And you can see I wanted to essentially install Node version 22. I want that to be installed in the micro VM that's going to be created as the runtime environment for this Lambda. I'm pointing it to where the actual code for the Lambda is. So this path name here refers to this folder here and this file, which we'll look at in a second. The timeout for my Lambda, we're saying is 10 seconds, which is probably way over the requirement. And remember, the timeout is the amount of time that the Lambda service gives to the micro VM to complete its task, i.e. to complete the execution of your Lambda function. If your Lambda function is still running at the end of the timeout, then the Lambda service will interrupt the micro VM, and it will return an exception back to whoever was the source of the event that triggered the Lambda in the first place, and it destroys the micro VM. Memory size, I was talking about that at the beginning. So that's essentially my CDK application. It just comprises of one resource, a Lambda function. Now, I am going to need to know what the name of the Lambda function is. So this line here, and you would have seen this in the EC2 project as well. This is essentially how we output something to the terminal when we deploy the stack. And I want to output, you can see over here, I want to output the function name that has been allocated to my function, my Lambda function. The Lambda service generates a name for your Lambda function, which is kind of different from this ID here. The name will comprise of the stack name, I think it probably adds on this ID to the name as well, and then it's a hash value as well added on to that. So if I deploy this stack, very little in it, as I said, but let's go through the CDK deploy as before. And as before, the CDK framework is creating the CloudFormation template, uploading that template to the CloudFormation service, and the CloudFormation service takes care of provisioning the resources that I'm requesting, which is my Lambda function, but it provisions some other resources as well linked to the Lambda function, like it creates an IAM role specifically for that Lambda function. It attaches IAM policies to that role. It links the role to the Lambda function. And there are probably one or two other very low level resources created as well. So it's completed its provisioning. And this here is the name, the full name that has been assigned to my Lambda function by the Lambda service. Now, how do I trigger this Lambda function? Well, one way you can trigger it is actually from the command line here using the AWS CLI. And the command to do that, maybe just before we do that, if we pop over to the Lambda service, and here we can see the actual Lambda function. Okay, and again, like I said, if we drill down into it, one thing we can look at, for example, is the code associated with this function. So if I go into this file here, okay, that is the actual JavaScript code associated with my Lambda function. And if I show you the equivalent in TypeScript, which is how I wrote the Lambda, this is the TypeScript code. And typically here is where you put the initialization code associated with your Lambda, but there is no initialization code required for this Lambda. And then the actual Lambda function itself is this part here. Now this Lambda doesn't do anything really useful other than it does execute a console log statement. And we have to find out where does that console log statement go. And it returns a HTTP response because everything is over HTTP when you're talking about things working in the cloud. So it's returning a 200 HTTP status code of 200 and an associated message, which is this message here. Now you can trigger any Lambda function from the command line if you know the full name of the Lambda function. And we got that. We got that here. We could also get it from the management console. So to trigger a Lambda from the command line, you use this AWS Lambda invoke, and then you give the function name. So now what I'm showing you here actually is, you can also pass or include a payload when you trigger a Lambda from the CLI. And the payload will essentially be included inside the event object that's triggering your Lambda. But that doesn't apply in this case. So I can just submit AWS Lambda invoke the function name. Now you also have to specify where you want to store the response that comes back from the Lambda. Okay, so if I just essentially, so I was playing with it earlier, but if I change this with the actual name that was given to my current Lambda, grab it again from here. So now I'll take this entire command. Now don't worry about this prompt here. This prompt is coming from the shell that I'm actually using. So it's unlikely you're going to get this prompt, but so what we're getting here now is this response here is actually coming from the Lambda service. This 200 response is coming from the Lambda service because when I submitted my command from the command line, that command essentially was to the Lambda service to invoke a function from me. And it seems because I got back a 200 response, the Lambda service is telling me that it successfully invoked the function and the function executed successfully. Right, that's all this is telling me. But and if I just type Q now to exit out of this, the actual response that came back from the Lambda function, that should be stored in a file called response.json. It doesn't really matter what you call this file. It does have to be JSON file, all right, but you can give it any name you want to. And so you can see here over on the left that I now have a file called response.json. And if I open that up, then what you're seeing here is essentially this is what was in the return statement from the actual Lambda function itself. In other words, this part here. Okay. So that all seems to have worked fine. The only remaining thing is, where does this console log statement go to? And the answer to that is that's actually sent to another service called the CloudWatch service. So what I need to do is I need to go to the CloudWatch service. CloudWatch is used by pretty well every other service uses the CloudWatch service. If that other service or one of the resources within that service needs to, log something, uh, then all of those logs are sent to CloudWatch and stored there. Now that applies with Lambda. If you've got a Lambda resource, i.e. a Lambda function, that executes a console log or whatever the equivalent of a console log is in other languages, because remember, our Lambda could be written in lots of other languages like Python or Rust or Ruby or Java. So they all have their own equivalent of console log. But those statements, uh, when you deploy, when they're contained within a Lambda function, those statements, the output of those statements is sent to this CloudWatch service. So if we go into it, now those of you that have studied some aspect of AWS before will be familiar with CloudWatch. What CloudWatch does is it creates what are called log groups. So there's a log group created for every resource that wants to use the CloudWatch service. Now we can see here that I have one log group. This log group is linked to the AWS Lambda service, and it's linked to this resource within the Lambda service. And you'll hopefully kind of recognize that this is actually the name of my Lambda function. So there will be, if you had 10 Lambda functions within an application, there would be 10 log groups created, one for each Lambda function. And if we go into the log group, a log group is broken up into what are referred to as log streams. And if I scroll down, essentially in the case of Lambda anyway, there is roughly there is one log stream generated for each micro VM that's created by the Lambda service. So this log stream corresponds to the micro VM that was instantiated when I triggered the execution of my Lambda function from the command line. And if I go into the log stream, then essentially what you're seeing here, if you look at these bits here, right, the init part of the log stream corresponds to the initialization part of your Lambda function. Now, even though we didn't have we didn't have any code in the initialization part of our Lambda function, there is still a section of the stream reserved for it. The start part of the log stream relates to the start of your handler of the function execution, and then everything in between start and end will relate to any console log statements that you have. So we only had one console log statement. So if I expand this here, and if you look over here, so it looks like I had a console log statement that said, uh, sorry, well, here it is here. I was invoked, okay? And if I go to my Lambda function, then that is indeed what the console log wanted to output. Okay, so we will be using, and you will be using console logs quite a lot within your Lambdas, essentially as a debugging mechanism. And so I'm just showing you where to find the output from those console logs. It'll be in a log stream, which is part of a log group that's linked to your Lambda functions. Are there any questions about that, I wonder? No. Okay, back to my slides. So we've demonstrated using the CDK to provision what I'm calling a hello world TypeScript Lambda function, which is the entire part of my application, and we've invoked it and we've seen where the console logs go. Now, the title here is Lambda integration. By Lambda integration, I mean what other services can trigger the execution of a Lambda in general. And there are quite a number of them, not all of them, but there are quite a number that can be essentially the source of the event. Um, the source of the event that triggers a Lambda function. And we will come across some of these as we work our way through this module. So again, those of you that have studied some aspect of AWS before will probably be familiar with S3. S3 is a service, it's essentially kind of a file storage service. But it turns out that you can link and in S3, we talk about S3 buckets, and S3 bucket is kind of like a folder. You can link the changes that might occur in an S3 bucket. You can link that with the triggering of a Lambda function. So, somebody uploads a file to an S3 bucket. You can get the S3 service to generate an event and send that event to the Lambda service and get the Lambda service to trigger the execution of a particular Lambda function, for example. And the same applies with some of all of these other services that I've listed here. I'm not sure if these are all of the ones that can trigger a Lambda. There may be some newer ones that can do it as well. So there's quite a number of them. Now, in terms of what I'm calling the integration model, there are 3 integration models, and the services are using one of the 3 models. So, for example, the API Gateway service, which we will look at as well in this module, it uses the synchronous model. That's how it's designed. The S3 service uses the asynchronous model. The DynamoDB service, where is it? This one here. The DynamoDB service uses the poll-based model. And I'm not sure about some of the other ones. SQSNS and SQS, they use the asynchronous model as well. Or maybe SNS uses asynchronous and SQS uses poll-based. We'll actually find out when we look at those services at the latter end of this module. So there are 3 models of integration. The simplest one to understand is the synchronous integration model. And specifically, the CLI uses that. So I've just demonstrated that. So when I submitted my AWS command there from the AWS Lambda invoke command from the command line, the request was sent directly to the Lambda service. The Lambda service, provisioned the micro VM, the function loaded the function into it, the function executed, the function returned a response. That response came back to the Lambda service, and the Lambda service returned it back to my terminal. Now, my terminal was waiting until that response returned. Hence, there was a synchronous, and I'm illustrating it here kind of on the image, although I've left out the Lambda service now, that's kind of in here, right? Your CLI talks to the Lambda service, but it's a synchronous communication model that's used in the case of the CLI anyway, as in the CLI waits for the response to come back from the Lambda service. Yeah. Also, the SDK applies the same thing. So I could actually write a program, run that program from my local machine, and as long as that program was using the Lambda SDK, it could actually communicate with a Lambda function. And in that case, there would be a synchronous model of communication as well. Same applies to API gateway, which we'll look at later on. You can actually link a load balancer to a Lambda function. And there's also something called function URLs, which I'm kind of illustrating down here. You can actually get the Lambda service to generate a URL for a Lambda. That means you can trigger the execution of that Lambda from a browser or from any other HTTP client, and we'll see that in a moment. Here I'm illustrating API Gateway, for example, is a service that we will use in a few weeks' time. And so the way that kind of works is you can imagine that you might have a React app or some sort of web app running in your browser that can send requests to the API Gateway service. And the nature of the request is essentially telling this API Gateway service to trigger the execution of a Lambda function. The Lambda function executes and returns a response back to the gateway, and the gateway returns the response back to your web app running in the browser. But again, it's a synchronous flow of execution. Same goes with this function URL idea. And so I'm actually going to demonstrate that function URL style now. So the objective is we want to use the CDK to provision a Lambda function, which we've already seen how that actually is achieved. But as well, we want to get the Lambda service to generate a URL for our Lambda function. And that means now we can use that URL to trigger the execution of the Lambda. We can do it from the browser, or we can do it from using something like maybe Postman. Also with these function URLs, you can actually configure them to be private. And we'll see how that works as well. So again, if I go into demonstration land and that's what I can do and do all of it. I need to do a CDK deploy actually first. I'll do that from here for convenience. On rare occasions, CDK destroy, sorry, just may not work for whatever reason. It could be networking issues. In those cases, what you should do is go straight into CloudFormation, find the stack in question, which is this one, and just select delete here. And that's the same as doing a CDK destroy. So I'll let that work away. And in the meantime, I'll go back to here. I need to change branches. So if I look at my Lambda function hasn't changed actually. It's really the same as before, just a console log and a return statement. But if I look at the stack file, again, it has a Lambda function just as before, but there's an additional piece of CDK code, which is this bit here. And so this is allowing me to, I'm essentially kind of attaching a URL to this Lambda function or asking the Lambda service to do that for me. So add function URL, and for that particular method, you pass it a JSON object, but there are specific properties in this JSON object. You specify what type of authentication, if any, you want. And if I can show you that there are only two options available to us. and we get the nice hinting from TypeScript. So I can either say there's no authentication. The only authentication option you have available to you is AWS's kind of inbuilt SIGV4 uh, authentication. So that's the one that I'll pick. And you also have to specify the CORS configuration associated with the URL. I'm just saying it's completely open-ended in this case. Okay, so in this case now, I want my stack to output not the function name. I actually want the URL. You can see over here, I'm getting it to output the URL associated with the function, with my Lambda function. And that URL, as I said, is generated by the Lambda service. So if I deploy this stack, there's not a whole lot extra other than the URL, really, when we think about it. And while that's working, I'll also go back to CloudWatch, and something that I would recommend you do is to clean up your logs fairly regularly. Otherwise, it's possible that you might be looking at an old log group or an old log stream, certainly when you're debugging. So I'm just going to get rid of, okay, probably not really necessary in this case because there's only one, but it's a habit really that I am inclined to follow, and maybe you should as well. Okay, so that's deployed. And so you can see here, I have a URL, and this is the URL that the Lambda service generated specifically for my Lambda function. Now, if I try and invoke it, just going straight using the browser, then I'm getting a 403 forbidden. Does anybody want to suggest why am I getting a 403 forbidden response back from, this response is essentially coming from the Lambda service, and it's telling me you cannot invoke this Lambda function. Does anybody want to suggest why that might be the case?
You've no auth token.
Correct. Yeah, it's not authenticated. So now setting up the authentication using Postman anyway is it's a bit tricky, but I'll just walk my way through it. So I'm assuming people are familiar with Postman. So I've created a Postman collection here for myself, this one here. And with Postman, you at the collection level, you can define variables, and those variables then are accessible to any of the requests that you have within a collection. So for me, and it's pretty much up to you as to what you consider might be used for variable. But if I look at the variables, I've defined three variables. One is I've just called it URL. So I want to set this variable to the URL that was just generated there for my Lambda function. So I'm just going to change that. Now, the authentication is based on AWS's own SIGV4 authentication algorithm, if you like. And SIGV4 is based on, or sorry, SIGV4 kind of uses the access key and secret access key that you generated for your IAM user. In other words, if you go into your on your local machine, when you configured the AWS CLI, that was in last week's lab actually, then what you were doing was setting up this this credentials file that contains your access key ID and your secret access key. Now I'm showing these here, but I'll generate a new set of access keys after this lecture so that not ye, but anybody else that might be watching this video could essentially rob these and use them. But it's these two values here. You've got to, when you're using Postman anyway, you've got to use those. So I've just decided to set up two variables that contain those values, and these are the correct values. I set them up earlier. So they're my variables, and what you also need to do is, and I'm going to do it at the Postman collection level, is you need to declare kind of what form of authentication you want to use. So if I go into the authentication tab, then there are a number of options. There are a number of authentication methods that you could use. Okay, and you're familiar with some of them. Maybe the bearer token was an authentication option that you used in the web app dev module last semester. Well, one of the options you can see down at the very bottom there is the AWS AWS signature authentication method, right? So that's the one that I've selected. And when you select that, you have to also you have to specify what is your access key. And you can see here what I'm actually doing is I'm referring to the variable. This would have been blank initially, but I want to refer to the variable that I've defined at the Postman collection level. And the Postman syntax for that is, if you do a double curly brace, then it lists the variables that you've defined. And I'm going to select this one. I could have put the actual key value in here if I wanted to. You don't have to use this variables approach. Secret access key, similar idea. You also have to select what region you're targeting, in my case EUS1, and you also have to specify the service name, which is this bit down here. Okay, so you've got to set all of those up. And having set all of those up, if I now actually want to invoke my Lambda using the URL, I create a request. So I have a request created here already. So if I go into that, it's a GET request, and I'm referring to the URL variable. So that's going to provide the URL of this GET request. And also in the Auth tab, I've selected to use the authentication method that was selected in the parent being the actual collection itself. So this is just, again, as I said, specific to Postman. You create collections and then you create requests within that collection. So this collection of requests here are contained within this, these requests are contained within this collection, and we refer to the collection as being the parent of those requests. So whatever I've set up at the collection level, which as you just saw was AWS signature authentication and all that, that's all going to be used. And so finally now I can send my request to this URL, a GET request, and essentially Postman will take care of uh, including the authentication. It's probably an authentication header, but let's send it. And it looks back like I got back. Oh, I got back null. That's not good. Did I do something wrong? Let's Disappointing. Let's see. Maybe change. Oh, I know what's wrong. I didn't. Anytime you make changes here, you have to save them. I think that's probably what caused that. Let's try it again. Okay, so I got back this message. This is a message from the Lambda, and that should correspond to, if I look at my Lambda, yeah, so that corresponds to that. So that seemed to work successfully. Now, to prove that the authentication is actually being used, if I go to my keys, and let's supposing I take this one here and I just make a change to it. So now I'm invalidating the key. So I'll just get rid of the A there at the beginning of the access key. Save the change. Go back to my request. Send the request. And I'm getting a security which is being this message now is coming from the Lambda service because it's the one that's performing the authentication. There's no authentication happening inside my Lambda function. Equally, so let's go back to here and let's undo that change. Similarly, if I try and access the URL without any authentication, so I've got a second request here called public URL to get request to the URL, but in the case of authentication, I've said I'm not going to use any authentication, but clearly that's not going to work. So if I send my request, I'm getting back the forbidden. Again, that's coming from the AWS service telling me that you don't have any authentication. In the previous one, I did have some authentication, but it was invalid. The actual authentication header value that was computed by Postman was not a valid one. It couldn't decode it on the Lambda server side. Whereas here, I'm not sending any authentication header at all. And so that's why it's giving me the 403 forbidden. So that's just Lambda URLs. Now, having done all of that, I don't think you're actually going to be using the Lambda URLs. You will be using them in this week's lab, but beyond that, you won't be. Okay, back to my slides. So continuing on with the, if we just go back to here, right? We're talking about these integration models. The synchronous one we've talked a little bit about. So we've demonstrated synchronous using the using the CLI. We've demonstrated synchronous communication using the Lambda URL, and later on we will use API Gateway as well. The asynchronous integration, we'll see that later on in the semester, but some of the services that use this integration model would be S3, SNS, CloudWatch. And if we look at maybe the image as just one example of it, so the S3 service, so if you can imagine now, let's supposing I've got a web app running in my browser here, and the web app allows the user to upload files. Okay, so the user uploads a file, and that file is uploaded to an S3 bucket. So there's some code in my web app that is using the S3 SDK to perform this upload. We needn't worry about that. But I want on the on the occurrence of an upload happening to this bucket, I want this Lambda function over here to be triggered, right? And so I can describe that in my CDK code. We won't look at it today, but we may get an opportunity to look at it later on in the semester. And so the way it works is the actual S3 service, having received a file uploaded to the bucket, the S3 service will tell the Lambda service. So the Lambda service is my kind of box here, which is controlling the execution of Lambda functions. The S3 service will tell the Lambda service. It'll generate an event essentially and pass that to the Lambda service. And the Lambda service, what it actually does is it puts the event into an internal queue. And so if there was a high volume of uploads happening to this bucket, possibly concurrently, because there may be many users using my web application, uploading files to the bucket, so there are concurrent instances of the event being triggered, and the Lambda service is receiving those events. It puts them into a queue, and then it invokes the Lambda function. So the Lambda service actually invokes the Lambda function and gives it a batch of the events in the queue. And then my Lambda function processes each of those events. And the events will contain information about what file was uploaded to the bucket, essentially, plus some other information. It may write some stuff to a database as a result. We don't really care. Now, I'm saying this whole integration is asynchronous. And the asynchronous is, if you think of, here's the source of the event, if you like. Well, maybe I shouldn't use that term source now because S3 is really the source, but here's where this whole process was initiated in my web app in the browser. So that's kind of the client, and ultimately the Lambda gets executed. But the client over here, it doesn't wait until this Lambda function has completed execution, and it certainly doesn't receive the response when the Lambda has finished and it returns a response. The response actually is going to be returned back to the Lambda service. But this client over here, it never receives a response from the Lambda function. All it receives a response from is the S3 service telling it, I have received your upload. So if you think of the client over here on the extreme left and your Lambda here, those two components are communicating asynchronously, as in this one here is not waiting for this one here to complete its execution. And that's essentially what asynchronous communication is. The initiator doesn't wait for the processing to complete. So that's why we refer to it as asynchronous. Just some other aspects of this. I'm saying the Lambda service places, well, I've already mentioned that, sorry. The Lambda service retries. So it's possible maybe that this Lambda, so it receives a batch of the events from the queue. Maybe the Lambda, for whatever reason, crashes. Maybe it needs to talk to another service and that other service isn't available, or there may be some other reason, there may be something invalid in the event. If it crashes, then the Lambda service will actually retry it. And I think it retries it 3 times before it kind of essentially gives up. So it is possible that your Lambda function may be processing the same events more than once. And so you've got to ensure that the nature of that processing is idempotent, which I'm not going to go into, but I'm sure you've heard of this term idempotency before. Suitable when that's okay. So that's essentially one illustration of this asynchronous integration model. And as I said, the asynchronicity is when you compare the originator of the event to the processing of that event. Those two components are not communicating synchronously. The third model is kind of a variation on the asynchronous. One example of, so I'm mentioning some of the services here that use this event source or pole-based integration model. One service that uses it is DynamoDB, which is a database service. And so we just explained this example over here. So again, you've got some sort of a client. Again, it could be a web app, but it doesn't have to be. Some piece of code that's running. Or it could even be a Lambda that's running here, but it's something that causes the database to change. So maybe it just writes a new record to this database. And we want to trigger this Lambda function down here whenever any changes occur to the database. Okay, so this is the Lambda that we're interested in. Okay, there may be a Lambda over here, or it could be something else. Could be an external application or a web app running in a browser or a mobile app or whatever. But the parts to focus in on is this database, changes occur to it, and we want this Lambda to be triggered whenever changes occur. So we would describe the relationship between the database and our Lambda in our CDK code. Again, we'll see that later on in the module. And the way it works is, it's not, in this case now, sorry, I've lost my pen. In this case, the database does not tell the Lambda service about the change. Instead, the Lambda service asks the database periodically, have any changes occurred in your database? And it will respond with the various changes that have occurred. So essentially, the database keeps a log of the changes that are happening in the database itself, or the database service, DynamoDB, for example. It keeps a log and it sends that log as a response to the Lambda service when it polls it for changes. That was different in the case of the S3 bucket earlier on. The S3 bucket told the Lambda about the event, whereas here the Lambda service is asking the other service, DynamoDB, have any changes or essentially have any events occurred. And it receives the response, and again it puts those events into a queue and it invokes the Lambda, giving it a batch of the entries in the queue. So from there on in, it kind of works the same as before. But the difference, as I said here now, is that in this case, the Lambda service is asking the other service, have any events occurred since I last polled you? Okay, so that's just an example of the third integration model. We will see asynchronous and event sourcing later on in the module, but not for quite a while actually. Every service has an API interface, not just Lambda, but we're interested in Lambda right now. So this is what I'm illustrating over here. Here's my Lambda service, which is managing all of my Lambda functions. It has an API interface, essentially a web interface. And the Lambda service also provides an SDK. And so any other service that wants to communicate with Lambda service uses that SDK. So, and these would be typically the sources for the events that are triggering my Lambda functions. So the Lambda service provides an API interface, a web interface, and it has an accompanying SDK. And so whatever other service, and indeed, if you write a Lambda function and you want to trigger another Lambda, you would use the SDK. Those other services are essentially using the SDK, the Lambda service SDK internally in order to communicate with it. So, if I go back to here, for example, how does the S3 service tell the Lambda service about the event, the S3 service essentially uses the Lambda service SDK to tell it about the event. That's what's happening behind the scenes. Similarly, how does this API gateway service, how does it tell the Lambda service? We have to assume that the Lambda service now is in here. How does it tell the Lambda service about this request that has come in? Well, the API gateway uses the Lambda services SDK to do that. Okay, now back to our Lambda functions. When you create a Lambda function, the Lambda service creates what's called an IAM execution role and associates that with your Lambda function. And a Lambda function's execution role that controls what other services your Lambda function can communicate with. So this is different now to the integration stuff that I've just been talking about. The integration models are all about what other services can trigger the execution of your Lambda function. Here, though, what I'm talking about is what other services can your Lambda function communicate with. And by default, your Lambda function cannot communicate with any other service. If you do want to allow it to communicate with other services, then you have to associate an execution role, which is an IAM role. You associate an execution role with the Lambda function, and that execution role will have policies which control what other services the Lambda function can use. So this execution role, I'm saying it grants the Lambda function permission to access specified AWS services and resources within those services. In the language of IAM, there are a number of policies, predefined policies that the AWS platform has created for us, and we can use these policies just as a convenience. So, for example, there's a policy called the AWS Lambda base execution role. Well, it's a role, but it has a policy within it. If we associate that with the execution role of a specific Lambda function, then that means that Lambda can talk to CloudWatch. Now, too much talk, but if I go back to my management console to give you an illustration of this, and if I go into the Lambda service, so this is the Lambda function that's associated with the stack that I just deployed there, the stack that had that I triggered the Lambda function using the URL. So if I go into that Lambda function, sorry, that Lambda resource really, function is just part of the resource. So I'm looking at this specific Lambda resource that I provisioned. And I've already shown you that, you can look at the code, talked about that. But if I select within this management console configuration, and if I select permissions, and lo and behold, we have some information here about the execution role associated with this specific Lambda function resource. And there was a role, it looks like that there was a role specifically created for my Lambda function. And in fact, if I had a number of Lambda functions within my application, each one would have its own custom execution role created for it. Who created this? Well, the CloudFormation did essentially, under the instructions of the from the CloudFormation template that was created by my CDK code. Okay. Now, if I click on this, I will be taken in to, I'll be transferred over to the IAM service. Because look, if you look up here, I'm in the IAM service now. And I'm looking at this specific resource within the IAM service, which is the execution role that was created for my function. And if I scroll down, I can see that there is one policy attached to this role. And if you look at the name of the policy, AWS Lambda Base Execution Role, okay, it's unfortunate that I called it role. It's really a policy. And what does that policy allow my Lambda function to do? Well, if I select it, that this is another resource that was created. Well, it's actually a predefined resource that's just available, but it's an IAM resource. If I click into it, I'm still in the IAM service, and I'm looking at the details of this this IAM policy. And how can I look at the policy? Let's see. There is a way of looking. Oh yeah, over here I can look at this. These policies are written in JSON, and surprise, surprise, the policy is actually related to CloudWatch logs. Logs is AWS's kind of internal name for the CloudWatch service. So this, because my Lambda function has this policy associated with it via an execution role, that is what allows my Lambda function to execute console log statements successfully. If I detached this policy from the role that's linked to my Lambda function, then when the console log statement executes within my Lambda, the Lambda function is actually going to throw an exception because it doesn't have permission to talk to the CloudWatch service. Don't know if I could prove that. Could I prove that? If I, let's see, if I go back to, I'm not sure if I want to go playing with this now though. Let's see. If I detach, can I detach that? If I select that, and am I allowed to delete it? There should be a way, but I can't see it, obviously. I'll demonstrate this idea maybe later on with another Lambda. How do I delete that? Maybe it's not allowing me to delete it because it is a, oh, there, remove. Will that do it? Okay. Now, if I go back to my Postman, it's on the fly now though, and if I try and trigger the Lambda again, see. Shut that down. Back to my Lambda and go into permissions again. Just going to do a refresh. Go to the role. Doesn't have any permissions. That all looks okay. Try and trigger it again. Not sure now why that's still running successfully. I'll have to look at it later on. But I'll prove what I'm trying to illustrate there with another example later on. Probably should have played around with that beforehand rather than doing it on the fly. No, there's anything obvious that comes to me. I'm just gonna plow on. Okay, so that's execution role that controls what a Lambda can interact with, what services it can interact with. There's also something called the resource-based policies. And the resource-based policies that are attached to a Lambda, that controls what can invoke your Lambda. So I'm saying these resource-based policies, we use resource-based policies to give other AWS services or other AWS accounts permission to use your Lambda. Okay, so it's kind of from the invoking side. And so in general, an IAM principal could be a user or some other service. An IAM principal can invoke your Lambda function if either A, the IAM policy attached to this, to the principal, the IAM policy is associated with the principal, allow it to do that, or if this function's resource-based policy allows it to do it. So again, some other service or some other user can invoke your Lambda function if A, they have the necessary permissions to do that, or B, the Lambda function allows them to do that. So it's one or the other. And again, if I go back to the Lambda service and look at the configuration side of it, the permission side of it, you can see here there's also some stuff about resource-based policies. So this is the policies for this particular Lambda function, just as the execution role was the execution role for this particular Lambda function. Now, it turns out that this Lambda function doesn't have any resource-based policy, which essentially means no other service or no other user can trigger this Lambda. And that would be consistent because I didn't specify anything in my stack code. Okay, right, so we have a Lambda function. We can trigger its execution from the command line. We can trigger its execution using a URL if we specified that we wanted a URL to be associated with it. We know now that if a Lambda function has log statements or print statements, they go to the CloudWatch service, and we can find them there. And by default, every Lambda has the necessary permissions to talk to the CloudWatch service, even though when I tried to remove the permissions there, um, it still worked. Actually, something just came to me there now. Let me just do one other. No, I'm not gonna. I don't want to be delaying time now, really. Okay. Then finally, I talked about these two kind of roles, an execution role and this resource-based role, if you like. They control what a Lambda function can do in terms of other services that I can talk to, and also what other services can trigger its execution. Now, in the area of concurrency, um, so far I've been saying when an event occurs and the event is targeting a particular Lambda, then the event occurs, it's passed to the Lambda service, and the Lambda service goes away and creates, instantiate a micro VM and runs your Lambda inside it. But what if there is a high volume of concurrent instances of the event, or a high number of successive occurrences of the event in kind of rapid succession? What the Lambda service does in that case is it actually creates a micro VM instance for each Lambda that it needs to execute. So if we take the simple example, let's supposing there are two concurrent occurrences of the event that's targeting this particular Lambda here. What the Lambda service does is, just clean that up first. So I've got two concurrent instances of the event. The Lambda service will actually create two micro VMs and get each of the micro VMs to run the Lambda function, and it will pass one event to one of the micro VMs and the other event to the other micro VM. What it does not do is just create one micro VM and first of all pass the first event, wait for the event to be processed, and then pass the second event. It does not do that. It actually creates two concurrent micro VMs. So what we would say is that it scales up automatically to match the volume of events that are occurring. And that kind of scaling up can be to quite a high degree, but there is an upper limit to it. So this is really another way of what I'm talking about here is the fact that the Lambda service is scalable. It scales up based on the frequency of the event occurrences and scales back down again. In other words, it kind of gets rid of the micro VMs as they're complete their execution. Now, of course, it can't keep scaling up infinitely. There is an upper limit, and arbitrarily, to an extent, the AWS people decided that the maximum number of Lambda, the maximum number of micro VMs that any AWS account can have running at any particular point in time is 1,000. Okay, so that's across all of your Lambdas, not necessarily just one Lambda. So if you had an application that had 10 Lambdas and there was a high volume of events targeting each of those Lambdas, it would do the scaling up, but once it hit that 1,000 mark for the total number of micro VMs that it has running on behalf of your account, once it hits that upper limit, then it starts actually returning what are called throttling errors. And a throttling error is the Lambda service response essentially telling the client that it's too busy, really. It cannot deal with the new events that have occurred because it has reached this upper limit, this concurrency limit. Okay, so that's how the Lambda service deals with scalability. Um, and you need to be aware as well of this idea of throttling. So throttling occurs when essentially the Lambda service doesn't have any more capacity to create more micro VMs within your account. Yeah. Um, what you can do is you can set what's called a reserve concurrency for each Lambda function. So you might say, I want to set the reserve concurrency to be 10. And that means if the Lambda service has currently got 9 micro VMs currently executing that particular Lambda function, and another event occurs, it will create the 10th micro VM. If another event occurs immediately, then it won't create the 11th micro VM. It will now return a throttling error back to whatever the source of the event was. So you can specify this reserve concurrency on a Lambda function by Lambda function basis. The throttling error at the HTTP level is a 402 error. So there could be cases where you have a client, could be again, like I say, a mobile app or a web app or a desktop app that actually receives a 402 response when you try to trigger a Lambda from it using the kind of synchronous communication model. And so no, sorry, what did I call it? 402, 429, sorry. So 429 is essentially the Lambda service's way of telling you that it has hit the reserve concurrency or the maximum concurrency associated with your account if you haven't specified a reserve concurrency. Uh, in the case of asynchronous invocation, okay, let's not worry about that for now, really. What that means is, let's supposing in your AWS account you've got, say, let's say 3 separate applications. One application actually has a load balancer. You needn't worry about it. We've never used load balancers, but we do know that a load balancer can be linked to a Lambda function. So we've got a load balancer, and if it receives a request, it essentially wants to trigger a Lambda function. But let's supposing that there is a very high volume of usage of this particular application. So we've got, hundreds, thousands of users currently using that application, and they're all triggering the creation of micro VMs for a particular Lambda. And let's supposing that consumes your 1,000 limit. That means that let's supposing that same account, we've got 2 other applications. The other application, just in this case anyway, uses the API gateway, and that also has a Lambda associated with it. And we've got another application that has a Lambda that has a function URL linked to it. It means that because this application here has consumed your maximum concurrency, Lambda concurrency limit, it means that all of the users that are using these other 2 applications, they're going to be receiving that 40429 throttling response. So essentially, this application is um, is what's the word I'm looking for? It's kind of dominating your entire set of applications. It's kind of hogging the concurrency limit that's associated with your account. Now, how do we overcome this problem? Because presumably we would like all of our applications to be always accessible. They may be slow, but we want them all to be accessible. And in this scenario, these two now are not currently, it's not so much that they're not accessible, but they're just returning throttling responses. So the way we overcome that problem is by setting a reserve concurrency for this lambda up here, which I was talking about on the previous slide, and set it to be something less than 1,000, obviously. And in that way, then, okay, you know, this application may now have to start returning throttling errors, but at least these two other applications are still um, functioning to a degree. So the reason the AWS people introduced this reserve concurrency idea is to mitigate against this scenario occurring where one application is essentially consuming all of your Lambda concurrency, your Lambda concurrency limit. The last thing I want to talk about in relation to Lambda anyway is this notion of cold starts and provision concurrency, which is different now. Provision concurrency is different from reserve concurrency. But before we talk about provision concurrency, we have to understand what do we mean by a cold start. So when I started talking about Lambda originally, we said that a Lambda is comprised of two parts, essentially, the initialization code and then the handler function itself. Now, when the Lambda service creates the micro VM instance and loads your Lambda code into that micro VM instance, the first thing it does then is it executes the initialization code and then it executes the handler. That is what we refer to as a cold start. So whenever the initialization code has to execute, the micro VM goes through what we term a cold start. Now, I think I might have mentioned it before, but if I go back to let's see. If I go back to here, we'll do actually. Well, let's go right back to here actually. Let's erase that. Okay, event source creates event is sent to Lambda service instantiates the micro VM, executes the initialization code, and then executes the handler. If another occurrence of that event occurs, well, sorry, before that, sorry, it executes the initialization code and then executes the handler. Now, up to now, I've said, and then it just trashes the micro VM. Well, in fact, it doesn't. It actually holds on to this micro VM instance for a short period of time. And the reason it does that is it's essentially waiting just in case there is another occurrence of the event that needs to be processed. And if that occurs, then in that case, it reuses this micro VM. But in this second instance, the micro VM is not going to execute the initialization code. It's only going to execute the handler, the function itself. Because you'll remember that typically what the initialization code is concerned with is establishing connections with other services. And so if those connections are established, they don't have to be re-established for the second event that is to be processed. Hence, the initialization code doesn't have to be re-executed as long as it has been executed once. Now, when that second event occurs and the same micro VM is used, then we refer to this second execution of the micro VM as a warm execution. which is the opposite of a cold execution. A cold execution is when it has to execute the initialization code and then the handler function. A warm execution is when it only executes the handler function. It's also referred to as a warm start. So back to the slide that I was on. So that's the difference between a cold start and a warm start of a micro VM. And we now know when these occur. Clearly, the warm start execution is going to be faster than the cold start because, the initialization code doesn't have to execute. So there is a less of a latency associated with warm start executions than there is with cold starts. And that latency can be significant. If the initialization code has to establish a number of connections to external services, that is obviously time consuming. And so avoiding that is ideal, is desirable from a user's perspective because they don't experience as much latency. So is there a way that we can at least minimize the number of cold starts associated with the execution of a Lambda function? And the way you can achieve that is by associating what's called a provisioned concurrency with your Lambda function. So that's what I'm saying down here, that you can declare a provision concurrency, which is different from a reserved concurrency. You can associate a provision concurrency. And essentially what the provision concurrency is saying is it's telling the Lambda service to sort of pre-start or pre-allocate some micro VMs for this particular Lambda function, even though no events have occurred. Create a small number of micro VMs, load them up with the necessary code, and execute the initialization code as well, and have those micro VMs essentially reserved for any potential events that are going to occur. Okay, so there are just various kind of configurations that you can attach to a Lambda function. And clearly this one is all about improving the user's experience. The reserved concurrency setting is about ensuring that a Lambda function does not dominate or consume all of your concurrency limit. Right. There's obviously lots of other stuff about Lambda that we could talk about, but we're going to park it for a while, although we're going to be writing lots of Lambdas for the remainder of this module. So I want to park Lambda, the Lambda service, and I want to talk about another AWS serverless service, in this case, the DynamoDB service. And as its name kind of suggests, it is a serverless database service. It's not the only one though, but it's certainly probably the most commonly used one. And in terms of what type of database, it's a NoSQL database service. And we're all familiar with this concept of NoSQL. So that's the first thing, that's the first characteristic of DynamoDB. It's a NoSQL database. I'm saying here that it's a fully managed service. Fully managed is really a byword for serverless. Fully managed means you don't have to worry about setting up your database server, making sure that the underlying database server code is fully patched and all that sort of maintenance related activity. That's all taken care of by the AWS people themselves. So it's a fully managed service. It's highly available. what actually happens is when you create a DynamoDB database and you start writing data to the database, behind the scenes, the DynamoDB service will make replica copies of your database across three availability zones. That's you can't stop that and you can't control it. That happens by default. And so the reasoning behind that, or the reason the DynamoDB service does that, is to maximize the availability of your database to the clients. So if one availability zone happens to be inaccessible from a networking point of view, then the DynamoDB service will send your request to one of the other AZ zones that are associated with your database, and your request will be dealt with by the other AZ zones. And it's, the whole issue of making sure that each replica copy is kept up to date. All of that is taken care of by AWS. You don't have to programmatically, or you don't have to do any kind of configuration to do that. It's a schemaless database. Well, every NoSQL database could be categorized as schemaless. And schemaless means, hopefully schemaless means that you can have records in the same table that don't have matching structures. Yeah. I mean, if we contrast a relational database with a non-relational database, in a relational database, each record in a table has the exact same structure or the exact same schema, but that restriction doesn't apply to NoSQL, and it doesn't apply to DynamoDB. Also, and really this point here and this point here, both of these are just characteristics of NoSQL rather than DynamoDB. The second one is, that there's no support for joins. So this idea of foreign key fields, which we're familiar with in relational database, that's not supported by DynamoDB, nor is it supported by any non-relational database. And that's okay. Obviously, security is an important part of any database, and in the case of DynamoDB, and in fact other database services that AWS provides, the security side is all linked into the IAM service, which we've kind of come across every now and again. And again, I'm assuming people have done some studies on IAM in a previous module. Certainly the Irish students have. Perhaps the Nangen students do not have, but I'll cover whatever aspects of IAM I need to as we work our way through the other parts of this module. But suffice it to say right now anyway, that the DynamoDB service has lots of links with the IAM service for security support. And we needn't worry about this last point either. Now, DynamoDB does have its own kind of terminology, and some of it is familiar to us. Others terms are maybe just not are specific to DynamoDB. So a DynamoDB database is made up of tables. Well, we know what a table is. I'm saying each table has a primary key. We know what that is from the relational model. The primary key must be decided at creation time, at table creation time. When you create a DynamoDB table, that's pretty much all you have to tell it at creation time. What is the primary key property of the records in a DynamoDB table? You don't tell it about the other properties because we've already said that DynamoDB is schemaless. A slight change in terminology here. I'm saying a table's entries are termed items. So we don't use the word record When we talk about DynamoDB, we talk about items, but they're essentially one and the same thing, but it's just a terminology. Each item has attributes. That's the case with records as well. We talk about, excuse me, records having fields. Well, in DynamoDB world, we talk about items having attributes. Again, the schemaless thing tells us that the attributes of one item in a table could be different from another item in the same table. There's only one exception to that, and that is the primary key. The primary key attribute or attributes have to be the same for every item in a table. That's okay. The maximum size of an item is 400 kilobytes. So kind of limited enough, but there you go. Now, DynamoDB has its own type system, data type system, which is unique to it, I suppose, really. Although the first part isn't. Obviously, it understands scalars, and the scalar types are the ones that we're familiar with. It has the document type. So what this means now is that one attribute in an item of a table could be an entire document. And document here, think JSON document. A JSON document is a set of key value pairs. So a single attribute of a single item in a table could be an entire JSON document. It understands lists as well and maps. So you could actually have a list of documents or a list of scalars within a single attribute. And finally, it has the notion of a set type. Obviously, the difference between a set and a list is the elements in a set have to be unique, whereas in a list, they don't have to be unique. And from the set's point of view, the only thing it supports are sets of strings, sets of numbers, or sets of binary values. Looks like you can't have a set of documents. So these are the native data types that DynamoDB supports. And when we read data from a DynamoDB table, we have to convert these native types into the types that are supported by the particular language that your, in our case, our Lambda function is written in. But fortunately, that kind of transformation from the DynamoDB type system to the type system of the kind of client or Lambda function, that's taken care of by the DynamoDB service, although we have control over it from a configuration perspective. Now, the primary key part is very important. And there's also some specifics associated with it that we need to be aware of when we're talking about the DynamoDB service. There are essentially two types of primary keys I'm saying here. There's the simple type and there's the composite type. Let's deal with the simple type first. In the case of this simple primary key, it means that the primary key just consists of one attribute. And that attribute also has to play the role of what is called the partition key. Now, I'll explain where this term partition key comes in a slide or two, but it is something that is almost unique to DynamoDB. But for now, we can think of a partition key as just being a value that has to be unique for each item in a table. And that's really typical kind of primary key stuff. So the simple primary key, also referred to as a partition key, its range of values, I'm saying, has to be unique, and it has to have a very diverse range of values. a broad range of values, because that impacts on distribution. And again, I'll elaborate on this in a slide or two. In fact, if we just look at a simple example of this simple primary key, which I'm illustrating here, and it's your kind of 101 example. So this looks like a table that is storing customer orders. Nothing too exciting about that. And I've decided that the primary key for this table is going to be a simple primary key. And the particular attribute that I've chosen is, surprise, surprise, order ID. Yeah. And that indeed would have a broad range of values. So that's fine. That's the 101 example of simple primary key. I still haven't really explained what partition key is yet, though. That's all right. The second type of primary key is what's referred to as a composite primary key. And a composite primary key has two parts to it. It has the partition key part and something called the sort key part. And these are essentially two attributes now that, when combined, these two attributes form a unique combination within the table. So in this case now, it turns out that there could be a number of items in this table that have the same partition key value. Whereas up here, we said that each item had each item had a unique partition key value, and the partition key value only occurred in one item of the table. Whereas down here, the partition key value will be repeated in more than one item. But when you take the sort key with it, that combination is unique. So clearly you have to decide what should be the sort key and what should be the partition key. Partition key still has to be, have a broad range of values. What I'm saying here is that if we have a table that has this composite key approach, and based on what I've just said, it means that you will have a number of items in a table that have the same partition key value, but they will have different sort key values. And that set of items that have the same partition key, in the language of DynamoDB, we refer to it as an item collection. So an item collection is a group of items, i.e. records, in a table where each item has the same partition key value, but different sort key values. And therefore the sort key and the partition key combination is guaranteed to be unique. We're also told that they're grouped by partition key. Okay, that collection of items, we know for a fact that they will be grouped together in the same location in the database, and they will be grouped by their partition key value, and they'll actually be ordered by the sort key value. DynamoDB kind of guarantees that. And again, if we look at an example from here, so I'm using the same context, my customer orders, but I've actually decided that I want the primary key to be a composite key in this case. And the individual parts of this composite key is, sorry, this is the slide I want to look at. Here's my composite primary key. It still has order number. Where's order number? I think that's an error, is it? Oh, sorry, no, sorry, beg your pardon. It still has order number, and I've chosen order number to be the sort key. Let's not get into why now, just for a while. And I've chosen customer number to be the partition key. In the previous example, as in this one. Order number was the partition key. In this example, customer number is the partition key. But clearly a customer is going to have a number of orders. So this partition key is going to reoccur in a number of items. But because I've chosen order number as a sort key, when I combine order number with customer number, that's going to be unique. Now, why you might choose this composite key versus the simple key model for essentially the same data. The reason you might choose one over the other relates to what types of read operations does your application need to carry out against this data. If you know for a fact that you will only ever need to read individual orders, you won't need to read a group of orders for a particular customer. Okay. If you know that you will have occasions where you need to read a group of orders for a particular customer, then you should use this composite key approach. And we'll see why that is the case. So it relates to the nature of the read operations that you will be carrying out against this data. And again, just to repeat it, if you know, for example, if you know that you will need to read a collection of orders for a particular customer, then you should use this composite key approach. However, if you instead you know that that will never occur, you'll only ever need to read individual orders and you'll know the order number. In that case, this simple key structure would suffice. So it's important that you understand the difference between simple and composite for now anyway. And I've just given a kind of a broad explanation as to why you choose one over the other. I wouldn't worry about understanding that part of it at this stage, but you certainly need to understand the difference between option 1 and option 2. Okay, I'm out of time as usual. Before I wrap up, I'll go back to our website, into this lab here. Now, I think everybody should be able to complete this lab. Maybe not the exercise, but you should be able to walk through all of it. We've talked about standalone lambdas. We've talked about lambda function URLs. Now I am actually introducing DynamoDB into this lab, and we really only started talking about it, and I didn't expect to get that far in my explanation of DynamoDB. But because of the way these labs are written, you will still be able to complete these sections here that relate to DynamoDB, even though you may not be 100% certain of all of the code that I've given you, because we haven't talked about the nature of the code. You should still be able to complete it. The exercise, maybe you can hold off on that until our next lecture, which unfortunately won't be for 2 weeks, because as you know, next week is reading week and there are no lectures. So I expect people to have this lab, with the exception of the exercise, completed before I talk to you again in 2 weeks' time. And as always, I will be physically in the lab rooms assigned for this module tomorrow morning, if anybody wants to come along and meet face-to-face and ask me stuff face-to-face. Right. That's it. Okay, just in case there's any questions, I will wait and pause for a second. No. Okay, so I may meet some of you tomorrow, and if not, enjoy the reading week, and I'll talk to you in 2 weeks' time. Bye-bye.